This talk is about two different research programs that I've had since the early 2000s, looking at energy and then looking at agriculture. And in this Venn diagram in my mind, there was no overlap. I was either doing energy or agriculture. And through time, the circles got closer and closer until now it's clear that there's actually considerable overlap. So the food system accounts for a lot of fossil fuel consumption in the United States. I always knew that, but I wanted to look more deeply into it. And the other piece of this is that energy accounts for a substantial and highly variable share of overall food costs that we pay. So the intersection between food and energy markets really kind of suggests that public and private decisions are affecting one market are going to have spillover into effects to another. So what we're going to grapple with today are two questions. Number one, would increasing the share of the US population having diets that align with healthy eating, federal dietary guidance, reduce fossil fuel emissions in the US food system? How neat. And then number two, would a carbon dioxide tax improve diet quality? So we'll look at both of those things. And a lot of this talk comes from this exhaustive and fantastic study from the US Department of Agriculture, and also from my research. I did an article with my friend and colleague Suzanne that was looking at the economic influence on meat consumption in a global sense, which is another topic for another day, but then also looking at the follow-up that I published with Suzanne again in this book called Strongly Sustainable Societies, Organizing Human Activities on a Hot and Full Earth. Our follow-up we're working on now is actually looking at a China and India comparison as the two most populous countries on Earth. What's going on with that? So these two things, again, economics and how it influences agriculture, and then how it influences the energy prices are what we're looking at. So what is the issue here? The consumption of fossil fuels and then also nuclear power and increasingly renewable energy by the US food system was equivalent, if you can believe it, to the entire national energy budget for India, the second most populated country in the world. And it exceeded the combined energy budgets for every nation in Africa, on the continent of Africa. So energy costs are substantial. They're also highly variable part of food costs in the United States. So this intersection of food and energy commodities markets raises questions about how changing food choices, such as through nutrition promoting of healthy eating, and then also changing energy prices, maybe, for example, by withdrawing subsidies, or in this case, through a carbon dioxide emissions tax on fossil fuels. How do they relate? So what we're going to do is to examine the relationship between energy prices and food system energy use over time. And then we'll measure carbon dioxide emissions associated with fossil fuel use in the food system, in your diet. And then with this information, we can actually determine whether outcomes of nutrition promotion and a carbon dioxide tax could potentially be interrelated. So move down. I just heard of this. Have you heard of this? I've just heard of this yesterday. Bluff. It means bottom line up front. So I'm going to overuse it from now on. I like that. So in this first bullet, about 13.6% of fossil fuel carbon dioxide emission is from food consumption, especially in the United States. And food is more sensitive to energy price changes than other sectors, pretty much every other sectors. So if Americans made a minimal dietary shift to eat healthy, food system energy use would decrease by 3%. Doesn't sound like a lot, but by making greater changes from the current consumption, food system energy use could be reduced by 74%. Can you imagine that? Reducing 74% of the energy that we use in food. The second bullet, a tax on fossil fuel carbon emissions, essentially, would increase the cost of a typical meal by not that much, $1.70 for each $100 that you spend on food and beverages. And this is an average. So the estimates range from 20 cents at the low all the way up to $5.40 per $100 of food and beverages. that are eaten. So there you go. Bottom line up front. Thanks for coming. It's been nice. So let's look a little bit more at this. So up next, we're going to look at domestic fuel use in the United States food consumption. And it essentially produces about 800, give or take 820 million of the 6 billion metric tons of carbon dioxide emissions economy wide in the US come from fossil fuels. And this is disproportionate. And this total is attributed to the food system's above average reliance on fossil fuel energy sources. Everything we do in food is energy, from refrigeration to the mechanization of agriculture. It's all energy. And so even though 86% of energy consumption back in 2017 came from fossil fuels, the share of food system energy from fossil fuels was almost 95%. So this is all carbon emitting and a drain on our finite dwindling resources. So we're going to first do three things. First, we're going to integrate the materials flow accounting framework that's been adopted by the United Nations Statistical Commission into the existing US food system, into the accounting structure. Then we're going to use mathematical optimization. I'll shield you for the most part from that to model a couple of different types of diets, two healthy, one baseline it's called, which is kind of how we eat now, based on a lot of different data sources and a lot of different model specifications. And then we can trace the total costs that would be passed on to food consumers in the form of a carbon tax. Oh, yeah, right. Okay. So, energy in the US food system is obviously a lot. So, a systematic allocation of food system energy use is super complicated because there are a lot of interconnected processes. The input output table is a means to understanding these interconnections, also called an EIO, or environmental input output analysis. It's commonly used in materials flow analysis from the beginning to the end of whatever like economic good you're looking at. And it can be used to allocate fossil fuel consumption and subsequent carbon dioxide emissions systematically from production processes all the way to the final product when you're eating it. So it's a system for allocating fossil fuels and carbon dioxide emissions from the supply side or the production side, and then attributing them to the demand side or the final products. And there are two articles that I am quoting and citing in here. Hearst wrote a paper that said essentially that US household energy use is the largest, about 40% of our energy use comes from buildings, but 12% of our energy budget is attributed to our food, to the food system. And then Canning said that 15% of the US energy budget can be attributed to our food system, which is huge. And half of the growth in food system energy budget can be explained by a shift from human labor. So when we were working in the fields before mechanization, towards an increasing reliance on energy services as we mechanize, everything. Now we have robots that are working in the fields. We're not even picking anymore. So the per capita food availability growth and then population growth, both each rather accounting for about a quarter of the increase here. So some examples of what is involved in your food, how much energy. Meat. So a couple of examples of meat. I have some notes here because I'm not good at memorizing everything. Meat, about 13 megajoules per kilogram for chicken stew, up to about 220 megajoules for shrimp. Chicken, 35 megajoules, and this is per kilogram. And then beef, 70 megajoules, per kilogram. By comparison, energy inputs for vegetables, so in and of themselves, maybe that's not, interesting or useful, but by comparison, vegetables rank a lot lower. We said that, 220 megajoules per kilogram for shrimp. A carrot has 2.7 megajoules per kilogram, and greenhouse tomatoes have 66 megajoules per kilogram. Desserts, so looking at sweets, everybody's favorite. Desserts can range from about 18 megajoules per kilogram for different types of candies, 44 megajoules per kilogram to chocolate. I was at LA Burdick yesterday. Love that place. Honey is very low, 1.3 megajoules per kilogram. So obviously the solution to saving Earth is to make sure that you just eat a lot of candy. So there you go. So let's move on to some examples. So more looking at energy in the U.S. food system. Seriously, the first bullet, the U.S. food system, according to a paper in 2000 by Heller and Kellonian, says that 11% of our U.S. energy budget is in food. And the second bullet, and the food system used 19% of the US energy budget in the mid 2000s. So household operations accounted for the largest share of total food related energy flows. Rather than focus solely on energy in the food system and looking at energy use, a number of studies have started to assess environmental impacts and overall kind of sustainability of dietary choices. And this is another thing that I'll read paper. The definition of sustainable diets. Sustainable diets are those diets with low environmental impact, which contribute to food and nutrition security and to healthy life for present and future generations. Sustainable diets are protective and respectful to biodiversity and to ecosystems. They're culturally accessible. They are economically fair and affordable. It's another piece. And they are nutritionally adequate. Finally, they're safe and healthy while optimizing natural and human resources. So a few things here. In the first bullet, omnivorous diets, things that have fish and poultry, and a lacto-ovo vegetarian diet have fewer emissions than the average US diet, but it's going to complicate it because the second bullet, these diets use more fertilizer, they use more water, and they use more pesticides than a lacto-ovo vegetarian diet. So more energy use doesn't mean that there's more emissions. And while environmental impacts depend on where, so looking at local food versus domestic food versus international food, and then also how it's grown, whether it's conventionally grown, organically grown, and in an extreme case, biodynamically grown, foods are, however they're produced, it's common to assess the sustainability by looking at a specific food product, a carrot or what have you. So in total, the bottom line is that it is more environmentally friendly, it's more sustainable if we are eating vegetables than if we are eating animals and plants. And healthy really generally just is defined as a diversity of food with a de-emphasis on meat and an emphasis on fruits and vegetables. So greenhouse emissions in the United States have been hovering around 7 million metric tons per year. There's good and bad news to this. Based on preliminary data from 2020, which is obviously the last year we have data, the net economy-wide US greenhouse gas emissions fell by 10.3%. Great news. We went from about 7 million to about 5.1 million metric tons. That's just the United States, though. And the global picture is a little tough in that the global average carbon dioxide concentration in the atmosphere is now up over 400 part per million, which was, when I was in grad school, was taught to be the sort of game over threshold. We're now almost to 417 parts per million. So it's a mixed picture here. US is doing better, great, but globally we have still problems. So let's look at what's been going on. How have the trends changed in these two sectors of food and of energy, and what's driving these changes? Also, how sensitive is the food you buy to prices of oil and gas? You can speculate on the market, futures of fossil fuels, and how much carbon is in your diet. You can do a carbon footprint. There are a lot of cool calculators out there on the internet where you can calculate your ecological footprint on your diet primarily. And so are you ready for some data? Let's look at some data. Don't worry about this. This is just a look at the bones of the model that spits out the output that I'm going to give you some graphs of. So I just don't like to be black box. It just shows how the data was analyzed, and you certainly don't have to read over all of these. Most of them are citations anyway here, but the inputs to the diet are represented here in box A. And this is the references you can see at the bottom, principal data sources, things like what we eat in America, dietary intake portion of the National Health and Nutrition Examination Survey, And what happened in this model is that they were weighted to represent the United States population, grouped into 16 different age and gender cohorts. And so really the box A here in green is just a summary of the average daily intake in grams of over 4,000 different food and beverage items that we have for sale in the United States. Then box B here is a conversion of all of these cohorts' food consumption in grams to measure nutrient, caloric, and food patterns here. So this is, oh, sorry, that's box B here. So here, you take the diet choices, you put them into food profiles, and then over here, I'm just going to gloss over this. I'm not an econometrician. I just call it the show me the money side. And it is tracing money and energy from primary inputs, production, and sales. So you have the boxes, Roman numeral 1, 2, and 3 is the money and energy. And then boxes A and B is diet, and that comes into the output of the model. This is the output of the diet analysis, and it is called the integrated sustainable diet analysis. So what you're doing is you're putting different variables into both sides of this, and you come out with an integrated sustainable diet analysis. So let's look more at that. This is the FEDS, it's called Food Environment Data System, and it accounts for all food-related energy market transactions in our economy, and it's broken out by supply chain stage and also by energy commodity. So first we're focusing on overall food-related energy flows. So this is annual food-related energy flows. You can see in quadrillion British thermal units, those in the know, we call it quads. It's a huge amount of energy. I also wrote down a couple of comparisons. So one quad or 1 quadrillion British thermal units is the equivalent of 45 million tons of coal, or 1 trillion cubic feet of natural gas, or 170 million barrels of oil. So you're talking gargantuan sums of energy. And so this is our yearly food-related energy commodity consumption by supply chain stage. The supply chain stages are here. You see there's the energy, and this is a historical perspective. So we're going from 93 up to 2012. And so focusing first on the overall food-related energy flows, the totals were slightly above. So the sum of all of these things, 12 quads or 12 quadrillion BTUs between 1993 and 1998, the first part of this graph. And then over the next 4 years, food-related energy flows rose sharply, and they reached about 13 and a half quads in 2002, right here, this kind of inflection point here. This represents a 12% increase and represents about 14% of the US national energy budget. But then what goes on, so the supply chain, food service, food processing, commercial transportation industry group led this. You see over here the, legend here, and this was a combined increase of about 1 quad, or about 71% of the overall change. In the remaining 10 years, so going on to the second half of this, year-to-year measures of food-related energy flows were either unchanged or they decreased. So household food service, again, looking over here at the legend, led the decline, and it dropped each year, falling about 0.7 of a quad over that interval. And then food processing and farm production also trended downward over this period, declining about 1/3 of 1 quad by 2012. So more data. And if you take this by energy commodity, this is just a way to look at how much energy overall in quads, again, through time, we have used energy. And these are, pretty similar. You see that these lines are roughly subparallel. Most significantly, most of the energy that we use in the food sector comes from electricity, or has historically. And then the next largest, which pales in comparison, is natural gas. And we have petroleum, and then other includes coal, and then also includes renewables. Apologies, I wanted to skip that one in the interest of time. That is in the reference. So if you wanted to look at the reference to this talk, I'm happy to have you look at it. So the question becomes, is energy intensity in the food system in the United States sensitive to energy prices? And the answer is, drum roll, yes, this graph shows that a one-time 10% increase in electricity prices while holding the price of capital and labor constant would lead to a decrease in the electricity use intensity over 5 years. And this slide confirms this negative relationship between energy prices and the food system's energy intensity. What you can see here, you have electricity prices, a food related share of the energy budget. This is back again historically. And this is in dollars per million British thermal units through time. And this shows a clear pattern of growing national energy budget share during a sustained decrease in electricity prices and a declining share during the steep increase in electricity prices starting in the 2000s. So here is the food related share of the energy budget. And then here's the 3-year moving average price of energy. Also was going to skip over that. Sorry, took a couple things out of here to not complicate the picture. So evaluating nutrition, promoting a carbon dioxide emissions tax on fossil fuels to assess whether nutrition promotion through these dietary guidelines that the USDA puts out, the US Dietary Guidelines for Americans, and a hypothetical carbon tax are complementary. So let's use data and analysis that we just went through. Some of these graphs that you just saw that seem to be independent, but then let's start to analyze the effects of each program on the aggregate dietary quality, so all the food and total energy use. Or in other words, let's look at the ways to meet the US Dietary Guidelines for Americans in a sustainable manner. So the big question is, if we shifted to healthier foods, what would happen to energy consumption and what would happen to the price of things? So I'm going to show you 3 graphs. There's 2 on this page and then there's 1 on the next page. And this shows all the dietary constraints where the baseline falls relative to these constraints. So in figure 8 here, you have the baseline consumption of nutrient food products with a limit on consumption. So you have alcohol, cholesterol, you have saturated fat, you have sodium and solid fats. We're not supposed to have really any of these. They don't make for a healthy lifestyle. So there's just a limit. You're supposed to be in this gray area. That's where you should be. There's no goal, there's just a limit. And you see that when you're looking at limits, the average American exceeds wildly in 3 of these limits. And then figure 9 here shows the baseline consumption of things that have a goal. So instead of saying this is how many, you can't have more than this, this is a situation where you're seeing you have to have a minimum of this. Anything below is a deficit. And these are the healthy things, right? Linoleic acid, fruits, seafood, red and orange vegetables, all the things that you're told are healthy for you, beans and peas, whole grains, fiber. And you see in those foodstuffs that have a goal, in this case, there's an underconsumption of 14 of the 24 dietary components in, again, I keep referring to this baseline diet. That's what the model that I showed you analyzed of just what we eat, regardless of what we're supposed to eat. There's this disconnect between what we're supposed to eat and what we do eat. And this is a picture of what we do eat versus what we're supposed to eat. And now you have over here in this last picture, you have things that have both a goal and a limit. So you have to fall between this range. So we saw first the limits and we saw the goals, as much as you can, as little as you can. Now we have a range. Things like the vitamins that you are used to seeing on food packaging. The vitamins, also niacin, phosphorus, calcium, overall calories. And again, overall, our baseline diet, what we eat in the United States, misses the mark on 6 of these 20 constraints. I looked at this, I saw 4, but then there's a little teeny one here for alpha linoleic acid. And then down here, vitamin E, were just at baseline. You could easily say that these 2, the vitamin B6 and then vitamin C is also kind of at baseline. So we're not doing a good job with what we eat in this country. So if you run a diet optimization model from that first picture that I showed you, that is sort of different inputs of economy and food. If you're on a diet optimization model with a combination of constraint sets and objective functions, the two diets that emerge are the realistic healthy diet, which I'll explain, and then the energy efficient diet. And we'll look at the difference between these two. The realistic healthy diet, which is the model for this is just shows the data input, what's going on here, what are the constraints, what do you want this diet to look like? Well, we want these, we don't want these, and the objective function of the realistic healthy diet is to minimize the difference between what Americans actually eat when they go to Burger King or when they're, having their coffee at Starbucks in the morning, and what would be considered healthy. So you want to tinker at the margins and in a way that makes maximum impact for minimum change to have a realistically healthy diet. It's the shortest route to eating healthy. The restraints on this are both cost, you can see here, and also dietary. This is the most restrictive constraint set because it ensures that caloric and nutrient targets are met. It forces individuals to eat a diverse, omnivorous diet, but it maintains a daily food budget of $4.65 per capita. So very cheap. This slide really just diagrams the modeling approach. And the model results are called the realistic healthy diet because the model, again, minimizes the change from the baseline. So a lot of the same food items, Doritos, are being consumed in this realistic healthy diet. And this model results in 2,500 roughly food items being consumed. The next one, the energy efficient diet, is in this case the models of initiative or the objective. So this is for the energy efficient diet. These are the data inputs and these are the constraints. It's to minimize the amount of energy that's in your food, to minimize the BTUs of energy that go into producing your food while shifting to a healthy diet. It's in this case you have greater changes from the baseline diet, and that's allowed by the model parameters. It's interesting, only caloric and nutrient constraints are included because the cost constraint the authors realized was unnecessary because all of the resulting diets cost less than the baseline diet. So you don't need to filter for cost in a way that you would with the other diet. So energy and price optimization go hand in hand. So this graph, almost done with the graphs, this graph shows the results from both models for the total population, and it's using two metrics, BTUs here, and then cost. And the axes here, this is the BTUs, how much energy you save, and then the cost over here is how much money you save. The realistic healthy diet, remember that's the one that has a minimum change based on the baseline diet, reduces BTUs by 3%. And you can see by the green dot, it keeps costs exactly the same. But to put this in context, a 3% reduction in total diet-related energy use is equivalent to the annual gasoline consumption of 3.7 million United States vehicles. So if we made these teeny changes to our diet, it would be the equivalent of taking 3.7 million automobiles off the road in terms of energy savings and then resultant pollution. In the energy efficient diet, the cost decreased by $3.41 per person per day. And the BTU, this is what they're focused on, these authors, decreased by 74% compared to the baseline diet, which is this red line here. The problem with this, you might say, oh yeah, let's get on board, let's do this. It represents an extreme change. I'm going to show you the kinds of foods that you would be eating on these two diets. It represents an extreme food change in choices for the average American eating the baseline diet. So what would you eat? I'm going to show you two graphs like this, simpler graphs. And this one shows the detailed results for the realistic healthy diet and then the energy efficient diet relative to the baseline diet, which is in red. This first graph is in calories. And in the baseline diet, most of the calories come from grains. See over here, the baseline diet here, and then nuts and legumes. The largest contributor to BTUs in the baseline diet is sugar, sweets, So on the x-axis here, you have the calories. So the largest amount of BTUs is sugar, sweets, and beverages. We eat a lot of that in this country for reasons that we can talk about some other time. The realistic healthy diet, that's the one that optimizes on nutrition and tries to reduce energy. Although calories from grain products are reduced to 665 calories, grain products are still the largest contributor to the total caloric intake in the realistically healthy diet, about 31% of the calories. But grain products contribute a lesser share to the total embodied BTU because relative, to the baseline diet. The realistic healthy diet, the calories and BTU come from meat, poultry, fish, and mixtures of meat, poultry, and fish. So it's about 30% of the total BTU, only about 300 calories. So now we're looking at the same graph, but we are now looking in BTU rather than in calories. So these are quads again here. So now in BTU, the energy efficient diet results in a different ranking of food groups. Legumes, seeds, and nuts are the largest contributor to calories. It's about 26% of the total. So you have here the quads, very, very efficient in terms of producing calories and nutrition in a low energy way. So you eat about 26% of your diet is based on legumes, nuts, and seeds. And then grain products come next, about 24% of your total. So grain products, you can see here, if you trace this line over, contribute about half a quadrillion BTUs, or 22% of the total BTUs in the energy efficient diet, which is the gray one here. This is a little bit counterintuitive because the calories, if you look over here, from milk and milk products increase in the energy efficient diet. If you go back one to the calories, the energy efficient diet here. So we see this relationship because dietary consumption changes both in terms of food groups as well as the composition of food items within the food groups. So these results indicate that the energy efficient diet, the combination of milk and milk products, is less energy intensive here than the baseline diet. So the energy efficient diet favors milk and milk products that have a lower energy requirement per gram across all the production stages, and they're still able to conform to the caloric and the nutrient targets. So this highlights the importance of interpreting the results correctly, and the model chooses a different product mix, not just different quantities. Another way to examine the shift to the realistic, healthy, energy efficient, and then the energy efficient diets is percentage change from the baseline diet. This is the table here that you're looking at. Overall, substantial changes in each food category are required in both the realistic, healthy diet and the next column over, the energy efficient diet. If you're shifting from the baseline to the realistic healthy, which is that middle, baseline's not on here, the largest increase in calories is, again, in legumes, nuts, and seeds, whereas the largest reduction in calories, 96%, comes from fats, oils, and salad dressings. If you're shifting to the energy efficient diet, I don't know if you can see my cursor, but over here, shifting to the energy efficient diet, the calories from legumes, from nuts, from seeds also increases the most, this time 7-fold from the baseline diet consumption. And foods that fall the most in the meat, poultry, fish, and mixtures category reduced by up to the 90% in the energy efficient diet. So in terms of BTU here, relative to the baseline diet, vegetables increase most in the realistic healthy diet by about 73% here. And legumes, nuts, and seeds in the energy efficient diet increased the most, 212%. The largest reduction in these diets is in fats, oils, and salad dressings right here. So that's where you get your reduction in energy. And in the energy efficient diet is for sugar, sweets, and beverages. So this is, I don't think it's anything new that we're told how to eat in a healthy way. The good thing is when you eat in a healthy manner, this is a result worth highlighting. All the alternative diets include animal products. People say, oh, if you're a vegan, you could save Earth. All of these diets include animal products, and that suggests that animal products are a part of a healthy diet that is also energy efficient. And the healthy diets include food items that are meat, fish, poultry, and mixtures. They can potentially reduce BTUs compared to the baseline diet, getting rid of the sweets, getting rid of the fats. And that depends on the amount and type of the food items in the category. The energy efficient diet, the diet that reduces, just looking at BTUs, how much can we reduce the energy in our food? It doesn't include meat and poultry, but it does include fish, eggs, and dairy products. But this scenario where there's bad news here, kind of where all Americans, and I'm sure you can surmise this, will shift to a healthier diet is hypothetical. And even if we move to less energy efficient or intensive diets, it's a big challenge in America. Let's be honest, we're the land of the free. And Americans make food choices based, I don't know, in my opinion, mostly convenience these days, but also taste, preferences, your culture, habits, and a big thing is price. So how realistic is it that we would get to the energy efficient diet? It's pretty restrictive for you. I already showed that. I'm sorry. So, would the big question here would an a CO2 emissions tax influence dietary choices through a cost and price effect? The total diet purchases of Americans during the study period, that historical study period that I showed you, were between 3 billion for a low and 62 billion for a high in carbon dioxide taxes under the baseline diet, with an average expected tax revenue about $21.2 billion that we could get to use to fight climate change. Under the realistic healthy diet, those numbers shift to between 3 billion and $60.5 billion in carbon dioxide taxes that would be paid, with an average expected revenue of about 20.7 billion average. And then under the energy efficient diet, we would get between 0.8 billion and 15.7 billion in carbon dioxide taxes, and the average expected revenue would be about $5.4 billion. So these are the SCC tax rate. So I'm going to coin a new phrase, bottom line behind. Remember that the consumption of fossil fuels, and that includes oil and natural gas and coal, and then renewable energy and nuclear power, by the food system that we have in the United States, is on par with the entire energy budget for India, and it's greater than the combined energy budgets for every country in Africa. The energy costs in our food system are huge, and they're also really variable. We're looking at this, recently at market fluctuations in energy prices. That gets passed on in food. So the intersection, I hope you find, the intersection of food and energy commodity markets, so you're looking at food, energy, and economics, is fascinating. And it really raises questions about how changing food choices, this would come from the FDA and the USDA, promoting nutrition, promoting certain types of food, and then also changing energy prices. And in that case, again, withdrawing subsidies from the oil and gas industry, and then also placing carbon dioxide emission taxes on fuels, and how these things all relate to each other. So the conclusion is that research really shows that changing energy prices are a cause of year-to-year changes in food-related energy prices. Also, food industries, from farm production to food processing to food retailing to food services, are really more sensitive to electricity prices than non-food industries throughout the US economy. So food prices influenced by electricity. And electricity accounts for about 60% of the energy use in the food system. So that explains why the food system accounted for a 50% increase in the total US energy budget during a period of declining energy prices. Fossil fuels are linked to US food consumption, and they produce about 820 metric tons of carbon dioxide emissions per year, which is about 14%, I said this before, of the 6 billion metric tons of carbon dioxide that is emitted yearly. piggyback that onto Americans having a very diverse diet, over 4,000 different items, and any number of food combinations using those 4,000 items that people can choose to meet or not meet, as the case may be, the dietary guidelines. And if you trace the total costs that would be passed on to food consumers from carbon taxes, this third bullet here, an average meal would only cost between 0.2% to 5% more. So not a lot more. So after a carbon dioxide emissions tax on fossil fuel use, um, you wouldn't expect, I don't think, an outcome that would radically change the way people eat. So this last, sorry. Okay. So this last one, we grappled with briefly two questions today. And the first question is, would increasing the number of people following diets that align with the federal dietary guidelines reduce fossil fuel use in the US food system? The answer is definitely yes. So taking the right path, or at least a central path, I guess you could call the energy efficient diet over here in the central path. The second question we asked was, would a carbon tax improve the quality of diet? If you start taxing carbon and making energy more expensive, would people eat less unhealthy? This left path over here. The answer to that, based on the data, is probably no, unless the very far outside aspect of the models are true, or where you have huge changes in the price of energy and huge changes in, therefore, the price of food. So there you have it in a nutshell.